Hey, so hi guys, good morning, good day, grade 8 students. We're going to try to solve some problems involving special right triangles. This is an introduction to geometry and more specifically to the topics in trigonometry. Okay, so an introduction to geometry lesson and with a focus on trigonometric problems. So this on special right triangles and its applications. Let's try to solve one problem using trigonometry, what you've learned in trigonometry. Okay, so we have here an aviator flew 70 miles east from A to C. From C, he flew 100 miles north to B. Find the measure of the angle of the turn to the nearest degree that must be made at B to return to A. So how will we visualize this problem? Let's say that the aviator is here at point A and he is flying towards east, okay, at point C. Now he flew directly north, okay, at point B. Okay, so for this problem, we need to find the angle measurement at which the aviator would have to make a turn. Would have to make a sharp turn for his aircraft to go from B back to A. Okay, so let's write our given here. From A to C, the distance is 70 miles, and from C to B, the distance is 100 miles. Okay, this is our north, this is our south, this is our east, and this is our west. Now, for this problem, let's assume that we have a right triangle. Now, if there's a right triangle, and we have here two sides, and we're trying to find a specific angle. Let's say we want to find this angle, the measurement of angle B. Okay, since it is a right angle and this is a straight line, once we get the angle measurement of angle B, once we find that angle, we'll be able to find the measurement of this angle. Let's say this is point E. So therefore, essentially, we will need to find the measurement of angle EBA. What is the measurement of angle EBA? Now, if the measurement of angle B is missing, or the measurement of angle ABC is missing, what trigonometric ratio are we going to use? There are three main trigonometric ratios that we can use. The first one is so that sine is equal to opposite over hypotenuse, ka, which is equal to cosine, which is cosine is equal to adjacent side over the hypotenuse of the right triangle. Then we have the tangent function, or the TOA. So the TOA is equal to the tangent theta, and that's equal to the opposite side over the adjacent side. Now for this problem, we are given an opposite side, which is 70, and an adjacent side to it, which is 100 miles. We're not given any value for the hypotenuse. So if there's no value for the hypotenuse, the only trigonometric ratio that we're left with would be TOA. Okay, and again, what is TOA? Okay, so TOA is equal to tangent theta is equal to the opposite side over the adjacent side. Okay, so for this triangle, we have angle B as our reference angle, and angle B is missing. So we just write here, tangent theta is equal to the opposite side, which is 70, over the adjacent side, which is 100. There you go. And if we simplify 70 over 100, so that should give us tangent theta is equal to 0.70. So how do we solve for the value of theta? Solving for the value of theta, we need to use the inverse trigonometric ratios. Okay, and what are the inverse trigonometric ratios? They are the trigonometric ratios that you see that has a -1 raised to them. Okay, but they're not literally raised to -1. Okay, so that's a trigonometric function that enable us to find angles inside of triangles given two sides. Okay, and for this specific function, so we need to find the value of theta. So for this one, this is going to be 0.70. Let's try to erase that. So we need to find the value of tangent of the inverse tangent of 0.70. If you try to put that on your calculator, if you try to put that in a scientific or an online or even a smartphone calculator, if you have the function, so that should give us 34.99 or approximately 35 degrees. Okay, so therefore this is the measurement of angle ABC. Okay. Now, if this is the measurement of angle ABC, this is 35 degrees, and these are linear pairs, so what's the measurement of this angle over here? So that's going to be 180. The measurement of angle EBA is going to be 180 minus 35. And what's 180 minus 35? So that's equal to 145 degrees. So therefore, at what angle must the aviator turn to the nearest degree from point B to return to point A? So therefore, his airplane, his or her airplane, the aviator's airplane, must make a 145 degree turn. Okay, in order to sharply return to point B to point A. Now that's gonna be a bit challenging. In real life, that doesn't really happen because the turning is quite a slow process. It's a gradual process. It's not a sharp turn, because when it's a sharp 145 degree turn, so the passengers would get dizzy inside of the airplane. But for ideal problem's sake, so that's how ideal it could be. Like a plane could just suddenly turn 145 degrees, but in real life, again, so it's a gradual turn, and it's much more complex than just an aviator suddenly turning 145 degrees. There has to be some adjustments so that the safety of the passengers and the comfort of the passengers are taken into account when they are inside the airplane. Okay, so that's how we solve this problem, and let's have more of these problems, more applied problems in SOHCAHTOA, the trigonometric ratios, on our next video.